Hello, this presentation is for Cal Poly Pomona ECE 4304. My name is Gene Drumhiller, and my team members are Eduardo Espino and Ruben Rangel. We are Group K, and we were assigned the RC6 cipher algorithm. So first, a quick introduction on what RC6 is. The RC6 stands for Rivest cipher because it was made by Ron Rivest, along with his partners Matt Robshaw, Ray Sidney, and Yukin Lisa Yun, and they published the cipher back in 1998. They created the RC6, which was derived from the RC5 cipher, also made by Ron Rivest, to meet the competition requirements of the Advanced Encryption Standards, or AES for short. RC5 and RC6 algorithms are very similar in structure, using data-dependent rotations, modular additions, and XOR operation. This form of structure is known as the Feistel cipher because Feistel network uses a round function, which is a function which takes two inputs, a data block, a subkey, and then returns one output that is the same size as a data block. In the case of a proper RC6, it has a block size of 128 bits, although a block size of 32 bits and 64 bits is possible, and supports different key sizes from 128 bits up to 2040 bits, and by default have 20 rounds. So the RC6 was designed with three components in mind. It was intended to be simple, offer good performance, and be secure. Simple was preferred so cryptologists can analyze a cipher better, which the code was optimized for better performance. And obviously, as a cipher, it needs to be secure. From our research, there has yet to be no practical attack that breached the RC6. Changes from RC5 included using W-bit registers, usually done as A, B, C, and D, adding integer multiplications, adding quadratic equations, and fixed bit shifting.
Here is a diagram of the RC6 cipher structure, known as a Feistel cipher or Luby-Rakov block cipher, which takes two inputs, a data block, a subkey, and returns one output the same size as the data block. A more accurate title for RC6 will be RC6 WRB, where W stands for word size, R is the number of rounds, and B is the length of encryption in bytes. Typically, RC6 implies a number of rounds of 20 unless it is specified otherwise. RC6 works with 4 W-bit registers A, B, C, and D, and as we can see in the encryption description, it uses 6 basic operations: addition, subtraction, exclusive OR, multiplication, and left and right rotations. We also have here in the description, we also have the for loop for the number of rounds in the encryption process. Then, as expected, the decryption procedure follows the same process as the encryption, however, it is in reverse.
For the actual simulation and the code implementation of the RC6 algorithm, we obviously wrote this in BHDL, which is the language we've been using all semester, and we implemented it in Movado, which is the software we've been using. We use what's called a key expansion, which is just an expansion algorithm that basically expands a user-supplied key, and it fills an expanded array. We did find this code on GitHub. We saw that the developer that wrote the code actually posted it on there, and it was open source. So instead of writing it from scratch, we decided to just use this. For the simulation, we also used a 32 key size. We used 20 rounds and 16 block size. From what we can tell, this was the AES standard. It looks like most of the people that actually implemented this algorithm, that was the what basically what they used. We also found a few test cases online. We didn't really have anything to go off to ensure that our encryption algorithm was functioning as it was supposed to. So we basically just looked for some, and we did find a few test cases, and we ran our algorithm against those test cases, and it seemed to work fine. We received the outputs that we expected to receive. So I'll go ahead and play the demo. We did upload this to YouTube, so we can go ahead and watch it there. This video is to show the demo for our RC6 encryption and decryption algorithm in BHDL. We're running this in Vivado. We wrote the algorithm. We wrote a few different files. We have the encryption portion of the algorithm here. This will obviously encrypt any plain text, and then we have the decryption file, which is basically the same as the encryption code, just in reverse, pretty much. This obviously decrypts that encrypted text. And then we have our key expansion code. This code we actually borrowed from someone on GitHub. We did find it there, and it was open source and available to use. We did give credit to this person in our report. So I'm going to go ahead and run the first simulation, which is going to be the encryption. Let's go ahead and do that. We did write a few different test cases here. These are going to be, the plain text is going to be the input. This here is the input, plain text. These are the different inputs that we provided, and the block output obviously is what we expect to see. Here the ciphertext, what we expect to see after we run the encryption. So the first one I'm going to test is this one here. So the way we ran this simulation is we did struggle a little bit to run this in the way that we learned in class using a test bench simulation. We figured out a different way. We found this online and found that this seemed to work a lot better for what we were trying to do with our code. So we have basically this TCL script that we wrote, and I can just tweak this portion of it here to whatever inputs we want. And back in here, we go ahead and run this. Let me close out this one and run it again. So to run it, we just go here up to Tools, and we run the TCL script. Just select the encryption TCL file. Just give it a second, and it'll show us the results. So we expect this input and this output. So as you can see here, these are inputs A, B, C, D. It's basically these here broken up into 4 registers. And then these are the outputs, A out through B out. And as you can see, it does match. So it looks like that part of the code is working. Let me run it again using different test case. I can run this one here. Again, this should give us, for the input, it's just the series of zeros. And this should be our expected output. So, yep, looks like it worked as we expected. All the inputs are zeros, and then this is our output. So now I'm going to demo the decryption part of it. Basically decrypt what we just encrypted. Just need to set this on top. change this to the one that we just ran. Now we expect to see this as the input, and this should be our output. So you can see that worked. Inputs are this array here, and our output is just a bunch of zeros. So that's working as planned. So unfortunately, we did try to implement this on our FPGA board. We were having some issues getting it to work on the FPGA board. It seemed like every time we would tweak our code to try to get it to work, we ended up breaking something in our code, and we really wanted to implement the VHDL and get it to work and actually do what it's supposed to. The issue that we were primarily getting was, as you can tell here, our input and output was at 185% utilization. So that was the main error we were receiving. As you can tell, everything else, all the other resources, LUTs, flip-flops, everything was pretty good. It was just mainly this input and output. We tried, like we said, several different methods, and we couldn't get it to work. We only had 210 I/O available, and we used about 388. So we do hope to try to get this to work in the future. We did enjoy working on this project, and we do hope that we can get this to work, because we would like to see it prototyped on a FPGA. Apart from that, yeah, it looks like this is here the number of LUTs and the flip-flops that we used. And the project did synthesize, as you can tell here. It's just as soon as we ran the implementation is when it failed. But again, we do hope to try to get this to work in the near future. So back to the slideshow. Again, this was the utilization. As you can tell, our lookup tables and flip-flops, the DSP, basically everything was pretty low, at about 3% or less, except for the I/O. That was the issue we were having with just even running the implementation, and we couldn't figure out how to get it to work. So again, that's why we just stuck to our virtual simulation. And we do, like we said in the demo, we do hope that we get to try to implement this in the FPGA later. Basically, in conclusion, we were able to observe the efficiency of the RC6 algorithm. We did learn a lot, and we saw that it is more efficient than the RC5 algorithm, at least from what we've seen. And then our implementation, the VHDL code at least worked as it was supposed to, and so did the decryption. Again, just as we've said in the demo, we do hope to implement this on an FPGA board and get a prototype going. Eventually, we would like to learn more about VHDL, as we did enjoy the course. And we do hope to see if we can do anything to improve the performance and power of our implementation eventually. So we do want to thank you, Professor. This was a very enjoyable course, and hopefully we work with you in the future.